the plan here is just to say a couple things about each of these, and maybe I'll go a little more in depth in the Doubly robust stuff. And the slides will be posted. So I tried to provide enough detail for each of these topics so that who's ever interested can dig in on those. And of course, if people want references to papers or other things, please email me. So one of the things that I think doesn't get as much attention in RL as it does in statistics, especially biostatistics, is the idea of planning an experiment. And we talk about sample size and power calculations and biostats all the time, but it does come up in RL applications where, suppose you want to test an RL algorithm to make decisions in some kind of domain. So maybe it's in retail or something else. And they want to know, well, how much experimenting do we have to do before we can be sure that it's working or not working, and what kind of differences should we sort of be expecting to be able to detect, and so on. And so planning for sequential decision problems happens outside of biostatistics, but I'll give an example in clinical trials because it's certainly the most common, but it's becoming more important as we start spending actual dollars to run experiments, to get information, to build decision support systems. So I want to say a little bit about that, and I won't go through the theorems, but I will just introduce the problem and say something about the ideas. And the non-regularity stuff is in all of this. And so now hopefully there's a little bit of a foundation so that you can see those ideas being kind of used throughout all of these ideas. So here's an example of a treatment regime for an MS. This is a mobile health application for post-traumatic stress disorder in cancer patients. This is with Sophia Smith. And there's two decision rules here. So this is a two-stage decision problem. The first stage says if your distress score is greater than 3, then you get something called the cancer distress coach. This is the mobile health intervention. Otherwise, if your PTSD symptom score is more than 20, then you also get CDC, otherwise usual care. So this is the first stage rule. The second stage rule, it says if you're responding, then just continue whatever you were doing. Otherwise, if you had started on CDC and your PTSD symptom change is more than 3, then add mobile coaching or M-coaching. Else, if you started on CDC and your distress score is now more than 4, add FaceTime cognitive behavioral therapy or FaceTime CBT. Otherwise, get FaceTime CBT only. And this rule corresponds to data collected from a sequential multiple assignment randomized trial. So this is a sequential trial where there's multiple stages of randomization. So you can see here the schematic for the trial. So the R's are for randomization. And so patients enter the trial, they're randomized either the distress coach or standard care. Then they're assessed for response. And I think, I forget what response was here. Maybe it was at 6 weeks. But if they're a responder, then they just continue what they were doing. But if they're not a responder, they get randomized a second time. And you can see there's different options going through. And so every patient that completes a trial will end up in one of these terminal leaves in the tree, terminal nodes in the tree. And we want to take data like this and estimate a rule like this or some other form. And the question is, how many patients do we need, and what kind of guarantees can we provide for a particular sample size? Okay, so this is asking, how many patients do we need to recruit, or how many time steps do we need to take to ensure that we can estimate a rule and then provide some guarantees for its performance. So why is this a new and emerging problem? Well, the reason is that most of the time when we run clinical trials in practice, the sample size is based on some very simple primary comparison or a primary aim. And we power, meaning that we want to have a sufficient power to do a hypothesis tests for something simple, like compare the mean outcome of 2 non-overlapping treatment sequences, meaning, if you take the two pools of patients who followed these treatment sequences, there's no overlap. So it's just a simple t-test, very easy. This is a very clear criteria for power calculations. Test statistics are standard. There's no non-regularity here, very easy. And in practice, estimation of a treatment regime or an optimal policy is often done as some kind of secondary analysis. And the reasons are that it involves composite hypotheses. So if you want to say something like the optimal personalized treatment strategy is better than business as usual, that's a statement about the optimal policy, which we don't know. And so it's a composite null, or a composite hypothesis rather, that that lives in the space of policies, right? And it's unclear exactly which criteria that we should be using. So, it should be 1 or 2 or 3. and what should they be. And the test statistics are non-regular, as we've seen. So if we want to talk about the value function, for example, that's not going to behave nicely. And so we can't use sort of basic sample size formula. So what do people do now? They run their trial. So they run a SMART. They run their primary analysis. So maybe they just compare the first two treatments. They do a comparison of those two. And then they do a secondary exploratory analysis where they estimate an optimal treatment regime or an optimal policy, say pi hat. Maybe they do some kind of cross-validation to get a sense for its value. And if it looks promising, then they run a follow-up randomized clinical trial where patients are randomized either to the estimated optimal regime that was estimated from this data and a control, and then they compare these two. And because this is a new batch of data, this is just a simple comparison of treatment versus control. And so again, it's standard. And so we call this the estimate and validate paradigm. This is sound scientifically in the sense that you're not using the same data twice, but it's potentially inefficient because you've now run two distinct clinical trials. And so there's higher costs, there's delayed clinical impact, because anyone who's run a trial before knows that it takes years and years to sort of design and get it funded and then run it and then analyze the results and push the results out into the clinical literature and then finally ultimately into practice. And another issue is that pi hat may be of low quality. This is a concern, not just in the medical world, but in any RL problem. So we didn't size a trial to ensure that pi hat would be near optimal. And so what can happen is that because we didn't power the first trial, pi hat may be low quality. And so we don't run the follow-up trial. And so we miss out on personalization. And so that's bad for patients. Or it does look promising, but it's still far from optimal. So then we run the follow-up trial and it doesn't validate, so we fail. Or it's not near optimal, but it's better than what we're doing now. We run the follow-up trial, and then we decided that pi hat's the strategy we're going to follow in the future, even though it's very far from optimal, so we're leaving a lot on the table, so to speak, right? And so the ultimate consequence is poor patient outcomes, and potentially we're not generating as much clinical knowledge as we could. And so the ideal situation would be to run a single trial that allows primary aims to be answered and addressed, and also estimate and evaluate an optimal regime. And in an industry context, you might say, look, we should roll out an RL-based algorithm in this setting. And so what you might want to do is run an experiment where you're randomizing treatment, or maybe even you're adaptively randomizing, but at some point you need to be able to say, at this time point, I will be able to compare the RL strategy with business as usual and make a determination, and we'll be able to decide and then move forward. And so while I'm talking about clinical trials here, the same thing happens in other applications. And maybe I should say it's distinct from like just having a constantly adaptive algorithm that just is changing all the time. These more discrete things often happen in settings where you're trying to replace a human system with an RL system. And so you want to do that head-to-head comparison. Okay, and then you want to use the thing that you've learned. Okay, so why hasn't this been done before? One reason is that identifying subgroups, patients that will benefit from a given treatment, has a lot of negative connotations. So we all know about the reproducibility crisis and some of the scandals in terms of data snooping and other things that have happened in subgroup identification. There's a lack of reproducibility and generalizability, and it's generally viewed as having lack of rigor. And in the sort of clinical trials dynamic treat regimes community, there's a widely held belief that sizing a trial to estimate an optimal regime would require either an enormous sample size, or you'd be unable to guarantee sort of frequentist operating characteristics, meaning construct confidence intervals that deliver the right coverage, or tests that have the right, say, type 1 error, but are still powerful, or that it would be intractable without strong assumptions.
It's a question for Java that if you're already online, why don't we just simply consider continuous online adaptation?
Yeah, so in some settings, that's great, right? So I think advertising, you can do that. I think search, you can do that. But if you have a team of human experts and you're proposing something new where there's a lot of pushback, so that could be in precision medicine, or it could be in retail or somewhere else. And basically, you're going to, the only way forward to actually get something adopted in practice is to say, we're going to run a bake-off between RL and whatever it is we're doing now. And we're going to do that for some fixed amount of time. And we're going to specify ahead of time what the results have to be in order for us to decide which way we're going to go, then this has the same kind of feel. And I mean, I agree. Sort of from a theoretical point of view, all you really want to do is just be constantly climbing uphill. There's non-stationarity to be concerned with. There's all sorts of reasons where just being online all the time is sort of the right thing to do, but it's not necessarily the thing that will be done until there's sufficient buy-in from the community. So that's the reason, really. And that's what's happening here is that, you know, we can imagine a world in which you go to see your doctor, they enter all your information into an iPad or something, and then it immediately looks to sort of the state of knowledge, and it adaptively assigns you a treatment randomly based on what it thinks is best, and also what's going to generate information without much risk to you. And like that would be sort of an amazing feature, but so we still have to do things in these discrete chunks now, like running trials. And the same thing it happens in some parts of industry too. Does that help?
Yeah, and there's another question. I'm not sure if I fully understand the question, but is it useful to think of the following as a clinical trial? What is that? If the RL system can demonstrate these results over this time frame, then it is comparably viable. So I think the question is, can we sort of generically think of this type of situation where we have a bounded time frame and we have to demonstrate that RL is better than standard of care or whatever, business as usual? Can we just always think that we are sort of in a clinical trial setting?
I do, but I'm strongly biased. I don't know if it's useful as a general rule, but because that's where my background is and where my experience lies, at least a lot of it, I often think of things that way. I also think it's important because when you're doing these kind of comparisons and you're comparing it against a person making a decision, there's a lot of causal inference issues at play. So it is useful to have that mindset, I think, because causal inference is so ingrained in biostats literature because they may be making decisions on information that is not contained in the data, and that can really cause bias to creep in and so on. So I think it's at least one useful way to frame these things, but then obviously there are very brilliant people who think about it differently. And so, yeah, I find it helps me think about these problems, but I guess it's not strictly necessary. Okay. All right. So in terms of the goal here, and I won't get into the details because we're running out of time. I just want to touch on all these things. But our goal is to develop a sample size procedure that ensures estimation and evaluation of an optimal regime or an optimal policy that has performance guarantees. So I'm going to state what those guarantees are, and then I'll just say something about how we do it. And so we developed in the paper sample size procedures at two extremes. One where you make very strong distributional assumptions. That's one route you could take. And this implicitly excludes all this non-regular, non-standard behavior we've been talking about. Or at the other extreme, we only require moment and tail conditions, and we don't require any of the models to be correct, and we allow for non-regularity and non-standard behavior, and we still provide correct sort of sample size procedures. And then the idea is like you can interpolate between these. So I just want to say what the I'm going to skip ahead and just say, what are the criteria? These are the two criteria. So I'm just going to read these off, and then all these constants will become clear as I read them off. So we want to be able to choose a sample size n so that there exists an alpha level test of the null that the value of the optimal policy is less than whatever we're doing now. So this B0 is the performance of business as usual. So the null is that we aren't going to do any better by personalizing, and we want power at least 1 minus gamma, provided that in fact personalizing is at least eta better than what we're doing now. So we want a certain level of power if in fact there is a difference of at least eta in terms of performance. And the second criteria is that you want the probability that the performance of your estimated rule is within epsilon of the true optimal with probability at least 1 minus zeta. So you want n so that both of these things happen. One, you can say, is it worth personalizing in this context? And two, if it is the rule I learned, I want the rule I learned to be very near to optimal with high probability. And so in the remainder of this section, we go through how to do that. And the way that we do it is through confidence intervals for the difference between V opt and beta 0. And the idea is that if the confidence interval width is less than eta for the difference, then if the confidence interval doesn't contain beta 0, if you have a confidence interval for V pi opt, then you can reject the hypothesis, and you can also show that it has the right power. And the second thing is we use, we basically bound the difference between V of pi hat and V of pi opt in terms of the difference between V of pi hat and sorry, V hat of pi hat and V hat of pi opt. We use a concentration inequality there. So I wanted to bring this up because this is one tiny problem that we talked about with 2 stages, but this idea of how do we size studies for estimation in an MDP and more general settings, I think is an open problem. I think even in things like, bandits. There's a question I'll answer in a second. For bandits, we know how to do inference in terms of if you have a linear bandit, let's say, you can do estimation, and you can use sort of standard methods to get confidence intervals for the coefficients, let's say. But we don't, sample size calculations, I think, are still kind of an open problem, and especially for MDPs and say POMDPs. And so I think there's still a ton of work to be done there. And if you're using, not a randomized policy, but you're using some kind of online learning algorithm for a finite time horizon and then doing these kind of tests. So I think there's a lot of sort of interesting mathematical problems and conceptual problems. But there's a question, it says, isn't there a moral dilemma that discourage online learning in medical care? Yeah, so the question there is, there's certainly debate about adaptive randomization in these trials. So what do people do in practice? Well, one, I mean, the idea is that that some will argue, and it's been argued, that if you do this adaptation in a clinical trial setting, so here I'm not talking about that. Here I'm just talking about a randomized trial. But if you're doing an adaptively randomized trial, that you try to argue it's at least better, it is better than a randomized trial. So if the alternative is you're going to do Thompson sampling versus you're going to do just a coin toss, that on average the number of patients who get the best treatment will be higher in the Thompson sampling case than the simple coin toss. So people will make that argument. So Peter Thal has designed trials this way and then made that kind of argument in cancer. Then there's the flip side, which is, well, what about the future patients? So if I do some kind of adaptation, am I then going to hurt future patients by generating less information? So they don't, in a clinical trial setting, I don't have the question in front of me now, but there was this, part of it was, well, if you're just giving them a suboptimal treatment for information gain, if you deliberately gave them the wrong thing for information gain, even though you thought another treatment was better, that would be certainly a problem. But that's what, in a randomized trial, you're just tossing a coin, and the purpose is information generation for future patients. And so you are trading information for immediate reward. Although, you're supposed, the idea is you're also an equipoise, so you really aren't deliberately giving them something you think is worse. So if anything, though, if you're running an adaptive clinical trial, you should be increasing the probability of giving them the thing you think is better. So I hope that helps. There's a lot of interesting kind of debates that still go on if you look up the sort of ethics of adaptive clinical trials. And I'm sure I'm not getting all the nuance that the clinicians like to think about, but yeah. So
there's a clarification question for this slide. When you say pi opt, like is it within a class? Is it the opt within some value function? Yeah, what's the definition?
Yeah, so it depends on the setting. So if you're going to put a whole bunch of distributional structure on everything, then it can be the true optimal overall. But of course, you've put all the structure that implies a very restricted class of policies because you've put a bunch of parametric structure on the data generating model. In the non-parametric case, we don't make any of those assumptions. This is going to be the population analog of whatever algorithm you're using, which may not be optimal. It may not even be optimal in the class because you have this mismatch between, say, the estimation procedure and the true optimum, right? So it'll be defined as the population analog of your estimator. So if the models are correct, then this will be the true optimum. Otherwise, it'll be whatever your algorithm is going to converge to with an infinite amount of data. Yeah.
Thanks.
Other questions? Okay, so I'm going to skip ahead. Okay, and I want to talk about the next thing here, which is infectious disease. I feel like that is a thing that we can all relate to. So obviously we're not thinking about white nose syndrome anymore because we're all thinking about COVID, but I got involved in spatial temporal decision-making through Ebola and through white nose syndrome and malaria. And now we have been working a little bit on COVID, but I think there's just a lot of interesting open problems in the spatial temporal decision-making sort of world. And so just the background here, the problem we're working on is this fungus that kills bats. And it hasn't been in the press lately because now there's obviously much more human threatening diseases, but it's pretty devastating in terms of bat populations. It kills millions of bats. And here's a picture of a bat with white nose syndrome. So that's this sort of white stuff on its muzzle here and on its wings. That's this fungus that grows on them. And so we were approached by U.S. Fish and Wildlife about where they should put these artificial caves. So these are the interventions. And if you see this little figure here, that's a human. So you can see how big these things are. So they're very expensive. And the idea of these artificial caves is they can clean white nose syndrome off the bats and off the walls and so on in an artificial cave where they can't in a naturally occurring hibernacula or whatever. So the question was, where should we put these to control the spread of this disease over, as it's spreading across the United States? And, part of the issue is that we don't know much about the disease. And so, even as recently as when we were working on this, the disease had been spreading for a few years and they still didn't know whether it could spread in the summer or not. Bats are very hard creatures to study. But I want to give a sense for what the RL problem is and why I think this is an interesting area that could use more eyes and brains here is that, so here's obviously the United States, and I've marked these little outline regions here. These are counties that have hibernating bats that are susceptible to this disease. This is a disease that affects hibernating bats of certain species. It's color-coded by year of infection. So the outbreak here was in 2006 in Schoharie County, New York, if I'm remembering that correctly. And then it spreads across the Northeast and then starts to go across the Northwest. Now it's in Texas, it's in Oklahoma. But so you see the disease spreading, and the question is, okay, so if I tell you the status of the disease, I tell you something about each of these counties, and you have a very limited number of interventions you can apply. Suppose you can pick a subset of 10 of these locations or 20 of these locations and apply an intervention to slow the spread of the disease. Where should you put them, right? And so this has a lot of interesting components. One, there's the spatial dependence part. So there's spillover effects that happen, right? There's spatial dependence. There's obviously the disease dynamics. The underlying generative model itself is spatial temporal. There's high cost of the treatments. It's a combinatorial problem. So if you have, I think this is 1,100 counties or something, and you can intervene on say 20 of them, that's an enormous action space. And then there's also lots of partial observability here. The way that they find out an infection is in one of these locations. Actually, somebody goes out and crawls in a cave and looks to see if the infection is there. So there's all sorts of false reporting. And so it's a really complicated, messy problem. And I just think there's a lot of room here in terms of feature generation, in terms of graph embeddings to construct the right features for Q-learning. I think the causal inference side with spillover is really interesting. And so I was hoping to get people excited about this. Obviously with COVID, there's tons of problems that are relevant, for our daily lives. So what is the strategy here? What is the policy? It's a map from the current epidemic status like this to a subset of counties that we mark as high priority for treatment. Is there a well-defined trade? There's a question that's come in. Is there a well-defined trade-off between evaluating interventions in terms of slowing spread and modeling dynamics? Yeah, so it's a great question. So the ecologists want to know about the disease dynamics, right? But I think the policymakers want to slow the spread of the disease over some time horizon. and they don't care at all about learning the disease dynamics. So the people who are funding intervention strategies are worried about the billions of dollars in like agricultural impacts, because bats eat insects and insects destroy crops. And when the bats go away, we have to use more insecticide. And anyway, so there's not a trade-off that I think anyone would agree on. So most of these problems have multiple stakeholders who would disagree on what the priority should be. So, here we're looking at minimizing some cost. So the cost could be number of infected individuals, or it could be just a geographic footprint of the disease, or some measure of economic impact, or it could be a composite outcome with like economic impact, number, and then maybe say ecological diversity impact on that. And so you can come up with some kind of composite and then settle on it. But I don't think, if you looked at all the different stakeholders, they'd all give you different objectives. So here we looked at the number of infected counties as our objective, but there are certainly other choices. Okay, so there's lots of problems like this. Obviously, the spread of human disease, ecological management. So looking at where we should create conservation areas. Precision agriculture is really a cool area where they look at how to put nutrients into soil. They can do it at a 1-inch granularity or something now. It's pretty amazing. And they also have, if you haven't seen this, these adaptive targeted pesticide placements. It's not related to this necessarily, but it's a pretty cool precision agriculture application. Airline planning. So we've worked on intervention strategies for airline planning, where you might want to change how much time a plane spends on the ground, or how much time a crew has to get from one flight to the next, in terms of reducing delayed flights and delayed arrivals and departures. Okay, so why is this an interesting problem? Well, when you have a new disease, a new outbreak, there's very little or no data on intervention effectiveness, right? You have noisy, incomplete, sparse measurements. It's very high dimensional. In white nose syndrome, there's like 11,000 measurements per time point, looking at all the features at all the locations. Online estimation means that we have to decide what to do from a continually changing data-dependent strategy, as you all know, but this means the sampling distributions are complicated. In terms of computation, this is a combinatorial decision problem, so there's 2 to the L possible allocations if you don't have any constraints. And so enumeration here is not possible. And so, how do we make progress in these kinds of problems? What we have done so far has been 2 very simple things. One is looking at just modeling the dynamics and then doing model-based planning. That's the first thing. And the second thing is estimating equations based on Q-learning, and then doing some kind of Thompson sampling in that space. And we managed to get some regret bounds and some rates of convergence here, but there's still big open questions about, how do we do meaningful inference? How do we extract domain relevant content about what these policies are doing differently than human experts, and like how do we take away sort of lessons learned so that we can help people improve their intuition as they're making decisions about these kind of problems. And that's clearly a problem with COVID, right? So that decision makers are trying to decide, whether we should keep things closed, mask policies and so on. And how do we take RL type algorithms and then extract kind of information that they can use to make their own decisions? So it's not necessarily, so here in white nose, when it's with the disease with animals, you have a lot more freedom to make interventions. So we're running one of these now with pigs. We just got funded in North Carolina, where we can actually tell them what the intervention is, where to apply it, and they'll just do that. But obviously with human diseases, that's not how it's often going to work. And so we want to come up with models that generate new information that can be useful in informing sequential decision making. So I just want to I'm just going to show 2 pictures. The first one, the model-based planning. What do we do is we posit disease dynamics models, which we estimate with maximum likelihood. Then we do simulation optimization with the estimated disease models to estimate an optimal action, which we then follow. And then we observe the next state, and we just go round and round, right? One thing that happens here, I should say, is we do maximum likelihood estimation, but then we sample parameter values that index our dynamics models from the sampling distribution for the maximum likelihood estimator as a very poor man's way of doing Thompson sampling. So we don't have a proper prior or posterior. We don't want to parameterize. We don't want to run MCMC in these contexts. It's very expensive. And so here we do maximum likelihood and then use the sampling distribution as a surrogate for a posterior and draw our dynamics model, which is indexed by these two parameters, from that sampling distribution, treat those as truth, then do model-based planning, get our optimal rule, and then choose action according to that rule and then continue. So I just wanted to...
What do you mean by sampling distribution from the maximum likelihood? Are you running a bootstrap or?
So we're using actually you could do a multiplier bootstrap for martingale difference sequences. You could do that. Here we're using an asymptotic approximation to the sampling distribution because we have a smooth likelihood, and so we're just doing that. We're using results for the asymptotic distribution, the MLE, for dependent data.
So unlike the earlier parts of the talk, here the asymptotic distribution is actually part of the method.
That's right. Yes, that's right. And also because we're doing maximum likelihood there's no Bellman sort of equation in here. And so these are nicely behaved too. So we can get their sampling distribution and sample from it.
And the likelihood estimation is on the underlying dynamics model.
That's right.
Why there's no max in that. That's just some parameterized set of dynamical systems.
Yeah.
Okay.
And the question was, when we say observe S, is this from the dynamics model or from the real world? This is from the real world. So you make the decision and then you actually see what the next state is. So this is happening in the real world. Yeah. Okay. And you can get some, so there's some bounds there, which I'm not going to go through. We've had enough math today, I think. So I just want to say the other picture is exactly what you were getting at. It's sort of a bootstrap. So now we have an estimating equation like we had before, and we perturb it with multiplier weights, which we then solve for an optimal policy. So we have to do some optimization to actually solve the perturbed estimating equation, get it a policy, take the action according to the policy, observe the next state, build the estimating equation, which we perturb using multiplier bootstrap weights, solve it, get a new policy, and continue. So this is a semi-parametric variant of Thompson sampling, where again, we've used a sampling distribution of the parameters indexing the Q function as a surrogate for a posterior. And because we didn't want to, this is trying to avoid modeling system dynamics. And so this is another sort of, the reason I wanted to show this is to show that there's also a lot of room for improvement, right? So this is one very simple thing you could do, which is Q learning with some kind of perturbation to induce uncertainty so that you continue to explore. But I think that in these animal diseases, this is all fine, but I think that there's a lot of contexts where they're going to want a deterministic algorithm, something like UCB or something like a rollout where if you fed the same data into the algorithm, you would always get the same answer back. And so I think that that's a big open area here, because I think designing those kind of algorithms for these spatial temporal settings is not necessarily easy because of the combinatorial aspect. So if you're going to try to maximize directly over all possible actions, it's a huge space, and it's not, these things are not submodular or anything, so it's not trivial to do that. So I think there's a lot of room here to improve. You can get some, I didn't put it in the slides, but you can get some theoretical results for that too. Okay, so now I want to slow down a little bit and get into this, wait, hang on. I want to get into, I'm in the wrong spot here, sorry. I want to get into the Doubly robust stuff here. I'm a little concerned that I have the same slides, so okay. I somehow got flipped back in time here, okay. There we go, okay. So doubly robust methods for model free and model based. So this comes out of the spatial temporal problem. And although of course it's of interest in other places. So one of the things in these disease models is there are these disease ecologists who have their pet dynamics models. So they build these compartmental models of the disease, and they believe in these models. And if they think, if their model's not right, then there's some other variant of it that is right. And so this is really nice for early on in an intervention process, because you don't have any data. You have to bring structure in from somewhere, and so bringing it in from these domain experts is really useful. But there's also obviously this fear that by relying on these models that are heavily parameterized and are almost surely incorrect, that you eventually, as data accumulate, you would like to move away from that and go to one of these model-free methods. And so one thing I've always wanted is a doubly robust method that will work if you have either model-based or model-free. So there's doubly robust in the sense that if you don't know the Q function or don't know the propensity score, then you get correct inference. Here I'm saying, if you have a dynamics model and then you have a Q, let's say a Q function or a value function model, if one of those is right, then you get the same answer, and then if they're both right, you get efficiency. So it's a little bit different than the normal doubly robust stuff that we see, at least in some cases. So, okay, just a quick review. But I say model-based, what do I mean? I mean, you estimate the system dynamics, and then you use simulation optimization or some kind of, you use those model dynamics to estimate the optimal rule. And you impose structure that offsets a lack of data. So that's really important in something like an epidemic. And you also leverage scientific theory for the dynamics, and that's really useful. So you're bringing this additional information into the problem. When you talk about model-free, I mean, you solve estimating equations for the optimal policy without estimating the dynamics. So you're imposing less structure, which is potentially good, but then you're also potentially having more variance. So you're trading bias for variance. And it's harder to leverage the theory in these kinds of problems. So you can obviously leverage theory for feature construction. So maybe they can tell you what factors are important or what interactions, or you can try to use some of these disease dynamics models to infer what features might be important, but it's not very easy, and it's not so clear cut as if they're telling you what the model is up to a few unknown parameters. So can we somehow get the best of both of these is the idea. And this is currently in an open area. As I was saying to Ambuj before this started, this is something that we're working on now. So I just wanted to sort of brainstorm a little bit since I have all of you here. What do we mean? Well, it's specified dynamics model. So typically we're thinking a parametric model here. It doesn't have to be, but it's best to think about a parametric model because I think that's the most common case. And say some kind of a value function or a Q function or some kind of semi-parametric type approach. And the thing that we want to construct an estimator for pi opt that is consistent if either, but not necessarily both, the dynamics model is right or the value function is right. And so this is the idea. And if you get them both right, then you get an efficient estimator. So this, at least in the disease dynamics model context, where you have somebody giving you this parametric model, you're controlling the action selection. So the propensity score is going to be right because you know what it is. It's in your control. So if one of these is right, you get the right answer. But if they're both right, you get efficiency. So this is the thing that we want. It's similar in spirit to doubly robust estimators in statistics. These have also been used in CS, obviously. Emma and others have worked on this, and so I should say CS also. Consistent when either the propensity score or Q function correctly specified, and efficient if both are correct. Just quickly, here's the setup again. This is the same setup as we had before. Suppose that you have data S1, A1 through STAT, and then SIT plus 1. And so here I'm assuming IAD data drawn from some distribution P. It could be you just have one continuous stream of data, but I'm looking at the IAD case here. T is the observation period, so that could be some kind of follow-up period for a clinical trial, or it could be observation of interventions for a disease. And again, ST is the state, A is set of actions, which here I'll just assume are 1 through K. And the utility is some function of state, action, and next state, coded so that higher is better. And we'll assume everything's homogeneous and Markov, and we'll focus on deterministic stationary policies, pi, which maps states to actions. Okay, so this is the setup. And again, I won't go through the technical conditions. I just want to sort of give one idea here. So we'll look at the discounted reward case. So the value of some state S under action, under policy pi, is the expectation under pi of the sum of gamma to, this is a discount factor raised to the v power times u to the t plus v given the current state is S. And an optimal regime here will satisfy Vs of pi opt is greater than or equal to V of pi S for all S in pi. And then just a quick review of model-based estimation. Well, we posit some kind of model for the transition dynamics. I'll assume that the initial state distribution is known, let's say, and it's indexed by some parameter theta, which lives in some parameter space capital theta. You construct a likelihood, there's other methods, of course, but suppose you construct a likelihood Ln of theta, compute theta hat, which is a root of the gradient of the likelihood equal to 0, or the log likelihood set to 0. It should be equal to 0, sorry, and a root of this. And then for any pi, we can generate data under theta hat, the maximum likelihood estimator, to construct an estimator, say V some theta hat of S pi. And I'm going to assume that we're using, we're generating an enormous amount of data with some very flexible approximation architecture. So basically you get the value function under this dynamics model. So I'm assuming you're going to generate trillions and trillions of points, and you're going to use a very flexible, properly tuned neural network. And so this thing is the right value function for this policy if these were the dynamics. Right? Just to simplify the sort of exposition here. Okay, so is that clear in terms of the model-based approach? I'm making this seem easy when, of course, it's not. But conceptually, it's easy, I hope. Okay. In terms of model-free estimation, here we're going to look at the value function. So we'll posit some kind of model for the value that's indexed by some parameter, say lambda. So that's a vector of parameters. And so for every pi, you would have a different lambda. And we solve estimating equations based on the Bellman optimality equation. So here, 0 is equal to the empirical expectation of the sum from t equals 1 to t of a point mass. This should be a point mass. This thing is 1 if st is equal to pi of at and 0 otherwise. And this is the behavior policy. And the behavior policy is allowed to depend on the entire history. And here's the utility at time t plus gamma times the value at the next state minus the value at the current state times some weight function. Okay. So this just comes from taking the Bellman equation for the value and turning it into an importance weighted estimating equation here. And this is any function of st and pi. So remember, part of our goal is efficiency. So we want to make sure that we have an efficient estimating equation here. So the question is, what weights should go here? So I have a paper on this that uses one set of weights that are not efficient. So don't use those. So what weights should we use? Well, the optimal weights, say in terms of the theory of estimating functions, a la Gandambe and others, is the optimal weight psi st pi lambda is the expectation of the gradient of this function g, I'll say what g is in a second, divided by the expectation of g squared, all given s, so these are each given st. So here, g is this term here, everything but this. So g is the term inside of these braces times this importance weight. Okay, so that's what g is. This is a sum of gt from t equals 1 to t times this weight. So we're trying to figure out what this should be. This is the function g. So this is what we should set psi to be. Of course, we don't know this, right? We don't know. Now we're talking about model free. So we don't know what this expectation is, or this one, right? But we do have a model. So here's the nice thing. This will give us a consistent estimator if our value function is right, no matter what weights we put in here, as long as they're linearly independent. So we can put weights in here. The only difference is going to be how efficient we are. So the efficient weights are given here, but if we put other weights, we'll still get consistency. So what we're going to do now is we're going to estimate these expectations using our model. So what we'll do is we'll take this expectation with respect to our estimated dynamics model, and this expectation with respect to our estimated dynamics model, and we'll put that in as our weight. So the critical thing is, if our model's wrong, if theta hat, if our model based on theta hat is incorrect, we'll just get an inefficient estimating equation that's still consistent if our value function is correctly specified. However, if our model's correct, then these should be the efficient weights. At least they'll be converging to the efficient weights. So we're going to plug those in here. Okay. So now how do we combine these two things? So what we're going to do is we're going to look at a weighted estimator of this value function. So it takes as input, so it's a function of s and pi. We have lambda hat, which is a solution to this with these estimated weights. Psi of, oops, where's my mouse? Psi of theta hat. And so what we have here is we have e to the alpha hat times some kappa n. I'll talk about these in a minute. So there's some weights times a value based on the model plus 1 minus e to the minus alpha kappa n times a value based on our system dynamics model. Right? So we have a convex combination of our two value functions. One is based on the model. This one's based on the estimating equation with the efficient weights from the model. And so what you'd like to have happen here is that if the model's right, then you would like this term to go to 0, right? And so you put all your weight here. And if the model's wrong, you'd like alpha hat times kappa to go to infinity. And so e to the minus that would go to 0. And so then all your weight would go here. Okay. So how do we choose alpha? So to choose alpha, or alpha hat, we're going to set it to be the norm of this estimating function. But now what we put here for the value is the model-based. So this is an average over the data, but this is our model-based value function. Okay. And this would be psi hat theta hat from the previous slide here. Sorry. Okay. So, or it could be any function, but that's the one we're going to use here. So what happens? If our model is correctly specified, then this will eventually be a root. It'll be an approximate root, and asymptotically will be a solution to this estimating equation, which means that this term here will be converging to 0 as n diverges. If it's wrong, and we have a unique isolated minimizer of the Bellman equation, then this thing will converge to a constant. So what happens is that if we set kappa to diverge such that if this thing converges to a constant, then alpha hat times kappa diverges to plus infinity. This obviously is non-negative. But we choose kappa sufficiently slow that if this thing is converging to 0, then kappa times alpha hat still converges to 0. So this has to be growing slow enough so that that happens. Then you'll get exactly what you want here, because this term here will go to infinity if it's wrong, and it'll go to 0 otherwise. And so you end up with this convex combination. So
if the system dynamics model is correct, then alpha converging to 0 makes sense. If it's not correct, then I'm just worried about sort of oscillatory behavior. So the fact that it actually does converge to a constant, is that because I have this IID replicates across n, or like would there be a problem if I only had a single trajectory?
I am looking at n going to infinity here. So that was yeah. So that is saving us here in some sense, because I'm using so if you use one single trajectory, I think you can still work things out. There's going to be a few challenges here. One, the estimation of theta hat's going to be much more troublesome. So that's one big problem. And so you can't just sort of argue, well, theta hat's going to the right thing, and so I really will get the right value function for that theta, and then it will be a root. I think that, yeah, I think things get a lot harder in that case. I'm not saying it's not true, but I don't know if it's true or not, or what kind of adjustments need to be made. So I am relying on that. This is as n goes, not as t goes. Yeah. Does that help? Or I think the other thing to note is in a spatial problem, what you want is you want the number of locations to go to infinity. So you may have one long trajectory, but you want to pool over locations. And so the hope there is, well, you don't have IID data. If you have a Markov random field or some other kind of structure, you still get enough replicates that might save you from having this complex dependence between the action selection over time and the estimation of theta hat.
What does a trajectory mean in a spatial temporal?
Oh, so you still have you have t diverging. Just I mean, you have regular time progressing, but you also may have a lot of you might have a lot of spatial locations. Like in our case, in the white nose syndrome, you had like 1,100 locations, and so the number of locations is very large relative to time, and so you might look at asymptotic frameworks where the number of location diverges also, and so there, that ends up playing the role of n in some sense. If that helps. Oh, okay. So we have just a few minutes. Let me just say that, okay, so we choose kappa n so that alpha hat kappa n goes to 0 if the model is correctly specified and diverges to infinity otherwise. So basically, even if it does oscillate, if that thing doesn't converge to a constant, but as long as it's bounded away from 0, you're still okay. I should have said that, actually. It doesn't have to converge to a constant. It just can't converge to 0 if it's misspecified. We do require the estimating equation to have a unique isolated minimizer. The rates you want to choose depends on the structure that you have. Consistency follows immediately, but efficiency is much more difficult. There's hope. We use these Doubly weights, so we should hope to have an efficient estimating equation. Also, if you're looking at parametric models estimated by MLE, those should also be efficient, but we don't know for sure. So this is an open area. And I think that there's certainly room for improvement. I think this idea of a convex combination, of course, is maybe a reasonable place to start, but I think there's probably better ways to combine these two things. This is certainly a naive thing to do, and so I would love it if there was people who wanted to think about this problem and work on this problem. Because as I said, we're in very early stages. So I think maybe I'll just wrap things up here because we only have 3 minutes. And just say that the slides will be made available, links to the papers will be made available, and the technical details for these things are included in the slides for those who are interested. And also you can email me and I'll do my best to answer any questions. Oh, thanks.
Thanks a lot. That was a lot to digest, but it was also at the same time very interesting, especially this last bit. This idea of, because there are lots of places where you can put structure in RL, right? We can put it in the model or in the policy or in the value functions. And this idea that if one of my guesses is correct, then at least I'm consistent. And then if more of my guesses are correct, then I get something even more out of it. I think it's an very interesting idea. Let me just scan for questions. I don't think we have any pending ones. I see someone's typing something in Discord, so maybe we will have a question soon. There's something that I wanted to ask you now. It has escaped my mind. Oh yeah, so you're right. So going back to the spatial temporal. So you said you have like what, 11,000?
1,100 locations.
1,100 locations. And the trajectories are, what's the time scale? Like, they measure things of the order of days, weeks, like, and how much data, like what is T in those?
Yeah, so T there is years. So there's very few decision points in the problem. So they want to update their policy every year, and they have some idea about how much resources will be available, but it also changes based on their funding. And so they're looking to plan at like a 20-year time horizon or something, or a 10-year time horizon. And that's the setting. There's actually a lot of nuance there because that I kind of brushed over, which is or glossed over, which is that they're collecting this data over time throughout the year. So it's convenient to sample caves during certain times of year, but there's also more likely to be infections during the winter or other times. And so there's real serious, I think, sampling bias in that problem that we really didn't account for. And I mean, because we had to make concessions somewhere. And so that was one of the places we just kind of assumed that you observe everything in one chunk for the year, and then you treat that as more or less noiseless observation. But I think, there's a lot of room there in terms of having that systematic bias sampling and having partial observability, but the partial observability definitely is dependent on time. And so they're collecting data continuously throughout the year, but then you make a decision once every year. is the time scale.
I see. And in one slide you mentioned that I think in the W robust case for the value function estimating equations, you said let's just use some very powerful approximating class like neural networks. In the specific applications you work in, let's say the virus, the bat virus thing, like, is there any sense, like what kind of, I mean, there are other function classes as well, right? I mean, we have lots of non-parametric classes that eventually would cover all functions, right? But in different applications, some tend to beat the others. Do you have any input on that?
That's a good question. I mean, I don't know. I'm partial to random forest because some of the inference is tractable, which is a terrible reason to do something. But yeah, I don't know that it's easy to see what the structure of those things should be from a problem. Like, if you're taking a white nose, like what should be the right class of functions to use? I think that's an open problem too. So another thing is like, can we use, so like one thing we've done before is taken a bunch of dynamics models. From those dynamics models, try to back out what the Q functions are, and then use those as basis functions in building a more flexible estimator. Like, so those become, if you have Q function for model 1, Q function for model 2, Q function for model 3, those now become like feature vectors for a non-parametric method. So that's one thing, but I don't know a good way to take a particular problem and then say, oh, this is amenable to like, say, neural networks or boosting or random forest or something else. I guess I'm also partial to kernel type methods, again, because the hope is you might be able to back up some inference, which also ends up being important in the kind of things that we work on. So, yeah.
I see. There is a question. I mean, you can read it. It's on Zoom from Thomas Lieber.
Okay. So there's a question. Curious to hear your thoughts on evaluating medical interventions for RL, how they vary across stakeholders. Does the judgment of clinicians vary from FDA to admin to biostatisticians to patients to nurses, record? Yeah. So good question. This is a very important issue. So one of the things that I didn't talk about that I think maybe doesn't get talked about in precision medicine enough. So clinicians obviously want to maximize health outcomes for their patients, but they also really are concerned about how their time is spent. And by that, if we tell them, oh, we're going to give you this tool to help you make better decisions for your patients, but this tool is going to require you to spend an extra 20 minutes with every patient. That may not, the cost of that may be so high that they're totally unwilling to adopt it unless it's going to save lives, So there's a lot of like implementation costs that are there. Certainly if you're talking about stakeholders like some kind of insurance company or medical provider, some group, in terms of how much it's going to cost. So when we worked on this dental recommendation system with health partners, one of the things we looked at was how much the cost associated with an intervention strategy that was adaptive. So if you're going to say to some people, come back in 3 months, whereas before we were telling everybody come back in 6 months, well, that's going to be more expensive, right? People are coming back twice as often. So you have to have some other, patients that are coming back only every year, let's say, right? But on the other hand, there's long-term savings maybe if you're preventing serious procedures by being more proactive in oral health. So they care a lot about, they want their patients to do well, either because it's less costly from an insurance point of view, or also if we want to give them the benefit of being caring about their patients, the insurance providers. But that is a major concern. And so I was at a talk on this kind of, I can't remember the person's name now, but he does a lot of implementation work for mHealth and other kinds of, he works with hospitalists and that kind of thing. But his rule was that if you can't get a 3 or 4-fold reduction, I think, in terms of outcome, that no one will pay the adoption costs. So this is an important question that you bring up, and it doesn't get talked about enough, I think. Yeah. I don't know if that answers the question or not, but hopefully.
Eric, do you know of an actual study, either planned or maybe even completed, that had a primary aim that had something to do with like a dynamic treatment regime and sample size calculation when done? Like, is this still in the future type of situation? Or is this already happening or about to happen?
Oh, no, we have trials in the field using this kind of sizing methodology, and yeah, so it is happening. So we have one trial that's almost done now, that was run out of Northwestern on mHealth interventions, or partially mHealth interventions among adolescent men who have sex with men. And so there's this also gets to the previous question. So it's delivering these messaging, safe sex intervention on the phone, but then it escalates to potentially having CBT or other kinds of more expensive interventions for non-responders. And part of all of this is, well, if we're going to roll an intervention like that out and a national or international scale, cost is really important. So there's obviously, the investigators care about the health outcomes of these patients, but there's also this concern that to make that impact, it has to be cost effective. And so we should really only be intervening with expensive interventions if and when it's going to be most impactful.
Thank you. I don't see any more questions coming in, so we can. There is one on chat. Oh, that's just a discussion between the. There's an active discussion going on the chat between the attendees and attendees. It's not a fun, which is good. I mean, I think we've had a very active audience throughout the week. I hope it stays that way all the way through Friday. Okay, thanks a lot, Eric. That was a lot, 4 hours of speaking in a day with home and kids in the background. I know it's not easy, so I really appreciate.
Well, thank you. Thanks, everybody.
Thank you.
I'll just remind you, I mean, I think a lot of students, especially, they want references. So I'm asking all speakers to include them in the final version of the slides. So just, if you could do that, we'll be very happy.
Will do.
Okay. Thanks a lot, Eric.
Okay, thanks. Bye, everybody.